Welcome all of you. In the previous lecture, we have discussed mainly the mathematical background of Newton-Raphson method, decoupled load flow method and fast decoupled load flow method. Just refreshing, we have derived the main equations for Newton-Raphson method from our conventional Taylor series. We have included the Taylor series, or we have applied our Taylor series in power system. So we have also seen which are the main functions in power system. It is none other than active power P and reactive power Q. And the main two variables were the magnitude of the voltage V and the angle of the voltage delta. Okay, considering all these concepts, the various functions as well as the various variables, we have derived a main equation for Newton-Raphson method. And in that equation, the main or the most important part was Jacobian matrix, because the Jacobian matrix determines the answer, or rather the problem in load flow analysis. So we have included or incorporated certain assumptions to the Jacobian matrix so as to make it much more simpler. Okay, and by incorporating that assumptions, we discussed about one more method, that was decoupled load flow method, where the main assumptions were the active power P, and active power P mainly depends upon the angle of the voltage than its magnitude, and the reactive power Q mainly depends upon magnitude of the voltage than its angle. Later on, into the Jacobian matrix, we have included that assumption and derived the decoupled load flow method. To the decoupled load flow method, certain assumptions were again made to develop the fast decoupled load flow method. So we have seen as such the mathematical background behind all these methods. Now today's lecture we will be discussing the numericals, or rather a problem solving in load flow analysis using Newton-Raphson method and fast decoupled load flow method.
Now let's look into a problem using Newton-Raphson method. Even though in the syllabus it is specifically mentioned that qualitative analysis only required for Newton-Raphson method, in this lecture we have included a simple problem which could be solved with the help of Newton-Raphson method. So in the examination point of view, if time constraint is there, you can skip this problem solving using Newton-Raphson method. Still, we are moving along with this. Here is a question. Consider the three-bus system shown in figure. Each of the three lines has a series impedance, this value, and a shunt admittance of this particular value. The specific quantities at the buses are tabulated. Okay, now just like observing any question in load flow analysis, or like the way we did in the case of a Gauss-Seidel method, here also let's move on to the details of the question. And a figure, a single line diagram is also given. Bus specifications are given. Here it is given like real load demand, reactive load demand, real power generation, reactive power generation. So from this, what can we infer? What is this real load demand? Real means it is real power. It is nothing but P. And real load, that means I can write it as PL. It is something associated with active power at the load. Here it is reactive load demand. So I can write reactive means it would be Q, and load, so it could be QL. Now here it is real power generation. Again I can write real power, so it is P, and generation, so I can write it as G. Similarly, reactive power generation, it is Q and G. So I can say there is load, real power at the load side, real power generation. Okay, now the last column is about the voltage specification. Now let's see the first bus. The first bus, you have load demand, you have reactive load demand, but the the real power generation as well as the reactive power generation is unspecified. What is the net active power P is equal to? net active power P is equal to total active power what? Generated minus total active power of the load. Similarly for the reactive power. So here in this particular case, the real power or the active power generated is unspecified. That is, this term is unspecified. So you can say that the net active power is also unspecified. Okay. Similarly, in the case of reactive power, the generated reactive power is unspecified. So you can say that your reactive power itself is unspecified for the first bus. So for the first bus, P and Q are unspecified, whereas its voltage magnitude and voltage angle is specified. So what type of bus is this? Yes, this bus is slack bus because we have the magnitude of the voltage and we have the angle of the voltage. Okay, now considering the second bus. In the second bus, it is given load active is 0, reactive load is 0, real power generation is 0.5 and reactive power generation is 0.5. So what is the net active power here? Active power generated minus active power load, that is 0.5 minus 0, which is 0.5. Again, reactive power generation is 1, reactive power demand or the load is 0. So the net reactive power is 1 minus 0, or rather you got the value for P and value for Q, and its voltage is unspecified. Then what type of bus it could be? Here active power P and reactive power Q is specified, and the magnitude and the angle of voltage is not specified. So obviously this bus could be PQ bus or load bus. Now coming to the third bus, load active power is 1.5, the generation is 0. So total active power means 0 minus 1.5, that is minus 1.5. Now coming to the reactive power, the generated reactive power is not given, whereas the load reactive power is given. That means in this case active powers are specified, whereas reactive power there is no reactive power specification here. Okay, and the magnitude of the voltage is given as 1.04. Delta is not specified. So what type of bus is this? Active power is specified and magnitude of voltage is specified. So this bus is PV bus or generator bus. So this is the way you should approach a problem. Merely by looking at a problem, don't get upset or tensed. Just analyze the problem. The problem itself will convey you many details. Now coming back to the problem, another details are given here. Each of the three lines, that is, obviously it is a 3-bus system, and each of the 3 lines has a series impedance of 0.02 plus j 0.08. Remember, impedance is given rather than admittance. Impedance is given here. Also, a shunt admittance is also given. We will see to it what is this shunt admittance and all. Okay. Now one more constraint is given. Controllable reactive power source is available at bus number 3 with a constraint of this. This is a reactive power limit given in the question. So whenever a reactive power limit is given in the question, you should understand that out of the buses given, one bus will be obviously generator bus. Why? Because only for this generator bus you will be seeing a constraint like this. Okay. Now, like the Gauss-Seidel method also, the first step is calculation of Y bus. Now, this is our particular bus. Okay, here the value of impedance was given. This 0.02 plus j 0.08 was given. 1 by that particular thing will give you the admittance. That admittance is marked over here. Fortunately, all the lines are having the same value of admittance. So then, one more thing is given. Total shunt admittance is J0.02. Shunt admittance means if any admittance is connected from bus to our ground. Okay, and this value is actually what you call by the name shunt admittance. Okay, so total shunt admittance is given as J0.08. So for calculating the elements like Y11, Y1, Y22 and Y33, that is for the diagonal elements, you will be considering this shunt as well. Okay, and all the off diagonal elements you will be considering in the similar fashion, just like the calculation of fibers itself. And one another important thing which is to be considered is that for calculation simplicity, please to calculate the fibers in polar form for Newton-Raphson method, because in Newton-Raphson method we will be in the mathematical background derivation itself, you might have noticed that we have considered every element in its polar form, whether admittance, whether voltages, we have considered its magnitude and its angle. So we will be calculating the bus admittance matrix in the polar form with magnitude and with angle. Now again, the second step also remains same. The second step is initialization of bus voltage. Rule also holds the same. That is, how will we initialize bus voltage? We will be initializing the bus voltage by considering the magnitude of the voltage as 1 and the angle of voltage as 0. In the question it is given the slack bus, its value is 1.04 and its angle is 0. And in the second we'll be assuming the magnitude as 1 and we'll be assuming the angle as 0. In the third bus the magnitude is given as 1.04 and the angle we assumed it as 0 degree. So I can write as magnitude of V1 is equal to 1.04 and angle, that is delta 1, is equal to 0. Similarly, magnitude of the voltage V2 and magnitude of the voltage V3 can be written like this, with their corresponding angle being delta 2 and delta 3. I hope this much step is clear to you. These two steps are common for both Gauss-Seidel method as well as Newton-Raphson method. Only difference is that in Newton-Raphson method, we will be calculating the bus admittance matrix in polar form and we will be initializing the bus voltage as 1.04 angle 0 instead of 1.04 plus J0. Okay, that is the only difference here in the case of first and second step. Now moving to our basic equation. Hope you remember this basic equation that we derived for Newton-Raphson method. That is delta 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 V. What is this delta? Delta represents the unknown parameters of voltage angle, and this represents the unknown parameters of voltage magnitude, isn't it? Is equal to J1, J2, J3, J4. I hope you remember what is J1. J1 is dou P by dou delta. J2 is dou P by dou V. J3 is dou Q by dou delta. And J4 is dou Q by dou V. And in this here you had delta P and delta Q. And what was delta P? Delta P was nothing but P specified minus P calculated. Okay, isn't it? Clear? Now here, what about this delta? Deltas are unknown deltas and magnitude of V are unknown voltages. Okay. Now P, that is the active power P, they are the specified or the known values, and Q are also the specified and known values. That means you should remember that here you will be writing all the unknown parameters or the parameters to be calculated. Here you will be writing all the known parameters or the given parameters. I hope this is clear. Now here the known parameters of P, in which all buses P are specified? Yes, P are specified in the first bus, second bus and third bus. But we will be neglecting the first bus because the first bus is slack bus. We need not calculate anything for the slack bus. Okay, now in which all buses the reactive power specified? Q2. In Q3 is the reactive power specified? No, instead a reactive power limit is given there. Reactive power is not specified. So the reactive power is specified only for the bus number 2. Okay, so what all are our known values? P2, P3 and Q2. Now, this equation also we know, that is what is Pi, what is Qi. These we have seen in our previous lecture regarding the mathematical background of Newton-Raphson method. Now, to this equation, if you want to know what is P2, you will be substituting I with 2. So you'll be getting, instead of Vi, you'll be getting V2. Instead of Q is equal to 1 to N. What is N here? N is a total number of buses. For this particular question, what is the total number of buses? It is 3. So YIQ, VQ cos delta I minus delta Q minus theta IQ. So I am including the values over here. We can expand like this. Okay. So after expanding like this, similarly I can write P3 is equal to, by substituting the value of I is equal to 3. Similarly I can calculate Q2 is equal to this equation by substituting the value of I is equal to 2. So P2, P3 and Q2, these are the known values which we are going to calculate as well. Now after substituting all the given values, we'll be getting like this. That is, in this equation, if you can substitute now the values of y2 and v1, everything we know, right? Every values we know. After substituting this known values or the initial assumed values, you'll be getting value for p2, p3 and q2. Since these values are obtained after substituting the initialized values, you can write it as p2 raised to 0, p3 raised to 0 or q2 raised to 0. Now coming back to our main equation, what was delta P? Delta P was P specified minus P calculated. What are the specified values of P? P2, we have seen what is the specified values from the table, isn't it? P2 is equal to 0.5, P3 was equal to minus 1.5 and Q2 was equal to 1. And now we have seen what all are the calculated values. This is one calculated value, this is one calculated value, this is one calculated value, isn't it? So I can write now delta P2 is equal to P2 specified minus P2 calculated. So you got something. Similarly, delta P3 is equal to P3 specified minus P3 calculated. Similarly for delta Q, we can calculate. So you got now this matrix, delta P matrix. Which is that matrix in our main equation? This thing now we have calculated. Okay, we have calculated this. Now what all things we need more? In order to get this matrix, we need to know the values of this different Jacobian. That is Jacobian J1. What was Jacobian J1? Dou P by dou delta. How many P now we have? We have P2 and P3. So obviously dou P by dou delta means we will be having dou P2 by dou delta and dou P3 by dou delta. Now let's see how many deltas we have. So this is our Jacobian matrix. Now how many deltas? Delta means the unknown values, isn't it? How many unknown deltas do we have? Or which all buses we need to calculate the angle of voltage. For the second bus you need to calculate, and for the third bus also you need to calculate delta. So which all are the unknown values of delta? Delta 2 and delta 3. Now how many voltages you need to calculate? I mean magnitude. Do you know to calculate the slack bus voltage? No. What about the second bus? Yes. Voltage of the second bus I need to calculate. Now voltage of the third bus, do I need to calculate? No, because voltage of the third bus is specified. So which all are the parameters to be calculated? That is delta 2, delta 3 and V2. So which all are the elements to be calculated? The elements to be calculated are delta 2, then delta 3 and V2. Isn't it? These are the elements to be calculated, or rather I can say these are the variables. And which are the functions? Our function was P2, then P2 was there, then P3, then Q2. These are the functions. So how will be writing the Jacobian? We will be differentiating each function with each variable. So which all will be our elements? Dou P2 by dou delta 2, dou P2 by dou delta 3, dou P2 by dou V2. Isn't it? Dou P2 by dou delta 2, dou P2 by dou delta 3, dou P2 by dou V2. Similarly, dou P3 by dou delta 2, dou P3 by dou delta 3, dou P3 by dou V2. Here, dou P3 by dou delta 2, dou P3 by dou delta 3, dou P3 by dou V2. Now, again, for the next function, dou Q2 by dou delta 2, dou Q2 by dou delta 3, and dou Q2 by dou V2. So, dou Q2 by dou delta 2, dou Q2 by dou delta 3, and dou Q2 by dou V2. So, this will be our Jacobian matrix, where this entire thing will be your element J1, and this will be your J2, this will be your J3, and this is your J4. Am I clear? Okay. Now, how can I calculate dou P2 by dou delta 2? Because we already have the equation for P2, right? P2 into this thing. We just see what is this equation. Now we need to differentiate with respect this equation with respect to delta 2. So this term I'll be having cosine of something. So you'll be getting sine minus sine with respect to delta 2. So minus of this thing. And in this, do we have any delta 2 term? No. So that is 0. Here also I have a delta 2 term. So it would be minus. So minus sine. Now once you differentiate this, you know all the values. What is V2? Our assumed value of V2 is 1. What is Y21? This we will be getting from our Y bus. That is 12.13 was the magnitude. Here you will be writing only the magnitude, right? Angle will be included here only. Now, into V1, what was the value for V1? 1.04. Sine. Delta 2, what was the delta 2? 0. Delta 1 was 0. Theta 1, 2 means it is the angle from the bus admittance matrix. So, it is like this. So, after substituting, you will be getting the value dou P2 by dou delta 2. The first term you got. Now, how will we be getting the second term? Dou P2 by dou delta 3. The same equation of P2, if you are differentiating this equation with respect to delta 3, you will be getting the next term. So if you are differentiating with respect to delta 3, the first two terms will be equal to 0. So similarly, dou P2 by dou V2 means you will be differentiating that equation with respect to V2, and again substituting all the values that you got. Similarly, by calculating all the elements, you will be getting the Jacobian matrix like this. So you can write that delta 2 raised to 1, delta 3 raised to 1. What is this raised to 1? Because in our main equation we have seen it as raised to k plus 1. Since this is for the first iteration, we have substituted k is equal to 0. So you can write it as delta 2 raised to 1. So this is a Jacobian. This Jacobian matrix inverse into this matrix we have already calculated. And after doing this matrix multiplication, you will be getting the value like this. What does this indicate? This indicates delta 2 is equal to 0 point something, and delta 3 is this. Okay, what is this? This is not actually delta, it is delta. That means change in angle. So what is the new angle? New angle will be equal to previous angle. That is, new angle means delta 2 raised to 1 is equal to previous angle means delta 2 raised to 0 plus this change. Okay. So what was our initial value? It was 0. 0 plus what is now the change? The change is minus 0.023. Okay, so this is the new angle for delta. Similarly here also you got as change in the angle is equal to this much. So you got the change, you didn't get the angle, you got the change in angle here. Now what is the actual angle is equal to original angle plus that particular change. Similarly for the magnitude of the voltage also. Or is this the magnitude of the voltage? No, this is not the magnitude of the voltage. This is change in magnitude of the voltage. So actual voltage will be equal to initial value plus that change. Okay. So you got V2 is magnitude this much and the angle this much. So you can write as V2 voltage of the second bus after first iteration is equal to 1.089 angle minus 0.023. Similarly for second bus where the magnitude was specified in the question and the angle just now you have calculated. So this is how you solve a problem in Newton-Raphson method. Okay, so Newton-Raphson method is quite easy compared to Gauss-Seidel method. The only issue or only major calculation is associated with the calculation of the Jacobian matrix. All these elements you need to calculate. These are by differentiation and substituting the values that we have assumed. So we can say that the first step in Newton-Raphson method is calculation of bus admittance matrix, and that bus admittance matrix will be calculating in polar form. And the second step is the initialization of bus voltage, where we will be initializing the bus voltage in the same fashion we initialized for Gauss-Seidel method. Only thing is that here also we will be taking the value in the polar form. And this is our main equation for Newton-Raphson method, where this is the unknown, or rather I can say the change in the unknown, and these are the specified values or change in the specified values. So delta P means P specified minus P calculated. Delta Q means Q specified minus Q calculated. Similarly, we will be checking which all are the specified values and which all are the unknown values, and within our main equation of the active power and the reactive power, we will be substituting the values and we will be calculating the values. Finally, we are calculating the delta P and delta Q. Then our aim is to calculate the elements in the Jacobian matrix. In order to write these elements, first we need to know which all are the unknown values, and from the data specified we are going to write which all are the unknown values or which all are the unspecified values of different bus. With respect to these variables and these functions, we can easily write a Jacobian matrix. Once you write a Jacobian matrix, you can differentiate those particular equations with respect to the unknown parameter, and we can fill the Jacobian matrix. Once the Jacobian matrix is known to you, it is very easy. The unknown parameter is equal to Jacobian matrix inverse into delta P delta Q matrix. So this is not your final answer. In this answer you will be getting only the change in magnitude as well as the change in angle, and from that you will be calculating what is the original angle and what is the what is the original angle and what is the original magnitude. And likewise we can complete the Gauss-Seidel method, and this is mainly simply based on the mathematical equation that we have derived. Okay, now we are moving on to the fast decoupled load flow method. Fast decoupled load flow method is within the scope of our syllabus. Problem in fast decoupled can be asked. Now, before proceeding, let's recollect what was fast decoupled. In the fast decoupled, if you remember, our Jacobian matrix was quite simple, and the Jacobian matrix included mainly susceptance, two susceptance, and the other two elements, that is J2 and J3 was equal to 0. So in this fast decoupled load flow method, or otherwise called FDLF, fast decoupled load flow method, we will be calculating only the elements J1 and J4. all other steps that we have seen in the Newton-Raphson method will remain same in the fast decoupled load flow method as well. Now, we can move on to the question. Obtain the power flow solution and one iteration for the system shown in figure. The line admittance are in per unit on a 100 MVA base. Please do remember this data given. Use FDLF. FDLF means fast decoupled load flow, and the figure is also given. Okay, now let's start with analyzing this question. How many buses are specified in this question? This is one bus, this is a second bus, third bus. The total buses included in this particular system is 3. So your total number of bus n is equal to 3. Now let's see which all are the buses specified. So this is the first bus. This is the first bus, and to this bus it is already written as slack bus, and voltage is also written here, which means this is a specified magnitude and this is the specified angle, because this bus is slack bus, because in a slack bus only voltage and its angle will be specified. Now here we can move on to the second bus. To the second bus, it is not specified what type of bus is it, but instead there is one clue behind it. Here there is an indication arrow towards the bus, and it is given as 300 megawatt. So that means, what is megawatt? Megawatt is a unit of, we cannot say simply as power. Megawatt is a unit of active power or the real power P. So which means P is given and it is injecting something. Okay. Now another thing is given, 1.02. What can be this 1.02? Can it be the power? No. This 1.02 can be the voltage. Magnitude. Is the angle given? No. So active power P and the magnitude of the voltage V is given. So what type of bus is this? Yes, this bus is generator bus or PV bus. Now we can analyze the next bus. And in the next bus, the powers are not injecting. Instead, the powers are taken from the bus. Okay. Now 400 megawatt, again megawatt, which is a unit of nothing but a active power P. Another is 200 MVA. MVA means it is a unit of reactive power Q. Now voltage values are not given. That means this bus P and Q are specified. Voltage magnitude or voltage angle are not specified. So what type of bus is this? This is PQ bus or load bus. Now here some other parameter is given. What is it? Minus 50 less than Q2 less than 100 MVA. What can this be? Yes, this can be the limit of the reactive power of which bus? Is that of the third bus? No, it is given Q2. Q2 means something associated with second bus. So that means this is the limit given for the second bus. So obviously second bus is a generator bus. Is it clear? I hope the analysis of the question is clear to you. And whenever you get a question like this, please to analyze the question in this fashion. Which all parameters given, what can be this type of bus, whose magnitude is given, whose angle is given, whether the limit is given, any other constraint is given, like that. Completely analyze the question and then only we proceed with the problems. Okay, now moving further, obviously the first step is calculation of Y bus, and here it is very easy. Calculation of Y bus is very easy. Admittance is directly given, so no need to take any reciprocal. It is directly given as minus J20. This is 10. There is no connection like this. It is by mistake it came. So it is minus J10. This is minus J10. So no need to explain that. So Y bus calculation is very easy. And in fast decoupled load flow method, you need Y bus both in rectangular form as well as in polar form. Usually it would be very easy type. So this is that in rectangular form, and this is that in polar form. And remember, here it is in radian, not in degree. It is in radian. Now next step is initialization of bus voltage. How will be initializing the bus voltage? We'll be initializing the bus voltage as 1.05 angle 0. Here mentioned it as degree 0 degree or 0 radian, whatever it may be, 0. 1.05 angle 0 because it was a slab bus. And another case, the second bus was a generator bus whose magnitude was given. So I cannot assume it as 1. Instead, I assumed it as the value given itself. It is 1.02 angle 0. And V3 again 1 angle 0 because the values are not given. We specified its magnitude. We initialized the magnitude as 1 and its angle as 0. Now, just like the Gauss-Seidel method, whenever you have a generator bus, what will you do? You will calculate the Q2, isn't it? You'll calculate the value for Q2. How will you calculate the value for Q2? Because we know the equation for Q2 is equal to, right? From that equation, after substituting the values, different values, you'll be calculating the value for Q2. Once you calculate the value for Q2, what would be the next step? Yes, checking or comparing this calculated value of Q2 with respect to the limits specified. Remember, here you got in what? Per unit. Okay, but this is a limit. The limit is minus 50 less than Q2 less than 100 MVAR. That means here it is in per unit. Here it is in MVAR. We cannot compare. So what we need to do? You need to convert this MVAR to per unit. How will you convert something to per unit? Yes, divided by base value. And for that, the base value is given in the question as 100. So by dividing it with base value, it will be minus 50 by 100 less than Q2 less than 100 by 100. So it would be minus 0.5 less than Q2 less than 1 now in per unit. Now you can compare this value with this. So by comparing that value, you can see that the Q2 or minus 0.408 satisfies this limit. Once the limit is satisfied, what will you do? We will treat the bus as PV bus itself. That is, we will be treating the bus as generator bus itself. Now, like what we explained in the case of Newton-Raphson method, we need the next step is calculation of delta P and delta Q. How will we calculate delta P? Delta P is the specified P minus calculated P. What is the specified P? Specified P, second bus, Pg2 minus PL2, or in the second bus it is directly given as 300 megawatt. You remember megawatt. Again we are calculating everything in per unit, so we'll be converting it into per unit. That means 300 divided by 100, you'll be getting it as 3 per unit. Similarly, P3, what is the specified power in bus number 3? Refer to the question. You can see that it is minus 400 because it is a load bus, it is minus 400. So you can write it as minus 400 by 100, that is minus 4 pu. Now we are moving on to the Q3 specified. Whether Q2 specified? No, Q2 is not specified because the second bus is generator bus. Q2 is not specified. Only in the third bus Q2 will be specified. Again it is a specified minus calculated and its specified value was minus 200 divided by 100, that is minus 2 per unit. Okay, so these are the specified values. And what is our next step? We will be calculating the calculated values, that is the P2 calculated. You remember this step that we have done in the case of Newton-Raphson method. We will be calculating the P2. I will be calculating the P2 because we know the equation for the active power P. And in order to calculate P2, we will be substituting I is equal to 2 and we will be proceeding. Substituting all the values, we will be getting like this. P2 calculated, P3 calculated and Q3 calculated. What is our next step? Delta P, isn't it? Delta P is equal to P specified minus P calculated. Likewise, we will be calculating delta P2, delta P3 and delta Q3. Now what is the next step? Next step was, you remember our first decoupled load flow. Our next step was calculation of bus susceptance matrix. This was our equation. You remember, delta 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 V is equal to minus B 0 B 0 B inverse into delta P by V delta Q by V. Okay, So that means on expanding this, I can write it as delta Q. Delta is equal to minus B inverse delta P by V. Delta V is, I am splitting this matrix, this term and this term, isn't it? Delta is equal to minus B into this. Other term is 0. Similarly, delta V is equal to minus B into this. So that's it. Now, this B will be representing by B dash and this B will be representing by B double dash. Okay. So this B means the B which is used for calculating delta. This B means the B which is used for calculating delta V. So this is represented by B dash and another one is represented by B double dash. Now in this case, which are the deltas? Is there any single delta? No. In the second bus you need to calculate the angle. In the third bus also you need to calculate the angle. So you have two elements in the delta, that is delta 2, delta 3. Okay. So we will see this later. We will first see this matrix. And if we have delta 2 and delta 3 over here, obviously you'll be having P2 and P3 over here. Okay, so P2 by V2 and P3 delta P3 by V3. Now which will be this element? The first element will be corresponding to this and this. That is, this is delta 2 and this is P2. So the first element will be B22. And this element will be corresponding to this and this. Just like matrix multiplication. So it is 2 and this is 3. So it will be 2, 3. And this element will be corresponding to, you can say, delta 3 and 2. So it would be 3, 2. This element will be corresponding to this delta 3 and P3. So it would be B3, 3. So this is the matrix B dash. Okay. So this is the matrix. Now what about the next matrix, voltage? In which all buses do we need to calculate the magnitude of the voltage? We need to calculate the magnitude of the voltage for second bus? No. In the second bus, the magnitude of the voltage is specified as 1.02 or something. We need to calculate the voltage magnitude only for third bus. So you'll be having only one element under this. If here only one element, then here also you'll be having one element, that will be, since here it is 3, here also it would be 3. Clear? So delta V3 is equal to, here this element will be Q3 by V3. Now what could be this element? Here 3, here also 3. So this element will be B33. Okay, now we will see what is this B22, what is this B23, etc. etc. So we know that in the case of R plus J X, this is impedance. Similarly in admittance, what will we say? Conductance, isn't it? Or conductance G plus J plus J B, isn't it? So this is admittance, isn't it? So this is the real part of the admittance, this is the imaginary part of the admittance. So if you are writing an admittance in a rectangular form, then its imaginary part will be the susceptance. Am I clear? So how will be calculating B22? Now for that, let's see our bus admittance matrix. Moving on to the this is our bus admittance matrix. This is the first element of the admittance, that is Y11. This is Y12, Y13, Y21, Y22, Y23, like that. So if you want to know what is the value of B22, what is B? B is the imaginary part of the admittance. So what is B22? B22 is the imaginary part of the admittance Y22. From this, where is Y22? This is Y22. What is its imaginary part? Is it 30? No, it is equal to minus 30. Am I clear? And what is this actually? This is Y23, or imaginary part of Y23 means 10, that is B23, like that. Like that, from the admittance matrix we can easily write. See, B22, it is the imaginary part of the admittance Y22, it was minus 30. B23, it is the imaginary part of the admittance Y23, it was 10. Similarly, B32 and B33 we can write from the admittance matrix. So this is that susceptance matrix. Okay. Now what is B33? This element and this element same. That means minus 20 here. So here also it would be minus 20. So in this way you can by simply looking the admittance matrix, you can just copy the susceptance from here. Okay. So once all these elements are known, we can write delta to delta 3 is minus of that particular element, I mean matrix inverse into with all these values we know. From there you will be getting delta delta and delta delta 3. So again repeating, this is a change in value that we are obtaining. Once the change in value is obtained, what is the actual value? Is equal to initial value plus that particular change. Okay. Similarly, delta 3 is equal to initial delta 3 plus that change. In the similar fashion, you can calculate the magnitude of the voltage is equal to this particular matrix inverse into this. The same fashion you can solve. So see, all the values can be calculated like this. See, compared to the Newton-Raphson method, fast decoupled load flow method is very easy. Even this method is very easy compared to Gauss-Seidel method as well as Newton-Raphson method, because the calculations are much less. Also, the Jacobian calculation is very easy. You compare the Jacobian calculation of a fast decoupled load flow method with that of a Newton-Raphson method. In the case of Newton-Raphson method, the Jacobian calculation was a tedious task, isn't it? So it is much more simplified in fast decoupled load flow method. So we can move on to one more question. We can move on to the one more question and let's wind up with the fast decoupled load flow method. So for the same question, the reactive power limit is given as this. Okay, this is in MVA something, it is not in per unit. What was the first step? Calculation of Y bus you have calculated, and remember we need the Y bus in rectangular form also, it is not written here, but still you need to calculate it in rectangular form also. What was the second step? Second step was initialization of bus voltages, like this. In the previous case we initialized. Third step was the calculation of Q2, and since the same calculation steps in the previous question, it is not repeated here. In the same way you will be calculating the reactive power and you got a value like this, and this is a limit. Now we can say that this value violated the limit. What will you do when this limit is violated? When the limit is violated, we will be setting Q as the violated limit and treat the bus as PQ bus. Similarly, the way we have done within a Gauss-Seidel method. Okay, so once it is no longer a generated bus and it is treated as a load bus, we have to reset the second bus voltage as 1 angle 0. Now the fourth step onwards it is same. Calculate delta P and delta Q. How will be calculating delta P? Delta P is P specified minus P calculated. Okay, P specified values remains same, isn't it? Specified values doesn't change, it remains same. Then P calculated. Okay, and in that fashion we have calculated all this and the bus susceptance matrix. And in this case one more thing is that since we have two load bus, we need to calculate the magnitude of the voltage for two particular bus. So while observing this, you can see that the two matrices are same, B22, B23, B32, B32, B33, like that. Two matrices are same. See, again it is much more simplified, right? If you know one single matrix, it is same for the second case as well. So in the similar fashion, you can calculate delta 2, delta 3. In the similar way, you can calculate. So on summarizing, we can say that in the case of Newton-Raphson method or in the fast decoupled load flow method, the steps that we are following is quite similar to the Gauss-Seidel method for the first 2 or 3 steps. That is, the first step was calculation of bus admittance matrix. Here we will be calculating the bus admittance matrix in polar form, and the second step was initialization of bus voltage, and the bus voltages are initialized in a similar fashion, that is, the magnitude is assumed to be 1 and the angle is assumed to be 0. Now, then only difference is we'll be assuming everything in polar form here. And then onwards, if there is any generator bus, we'll be calculating the reactive power for that particular generator bus. We'll be checking with the limits given. If the limit is satisfied, it is proceeded as a generator bus. If the limits are not satisfied, we'll be setting the reactive power is equal to the limit violated and treating the bus as a load bus, and we'll be proceeding in the form of load bus. Okay. Now next comes the calculation of the Jacobian matrix, which is a little tedious in the case of Newton-Raphson method, whereas it is very easy in the case of fast decoupled load flow method. So in the university question, if a question problem in Gauss-Seidel method and fast decoupled load flow method is asked as a choice or something like that, I strongly recommend to you to opt for fast decoupled load flow method, because it is calculation simplicity is there in the fast decoupled load flow method. The the matrix also will be maximum 2 by 2 or so, and you'll be asked to perform only one iteration as well. Okay, so these are the steps associated with the calculation. Please do follow this step as well. Just like we have explained in the case of Gauss-Seidel method, please prepare an algorithm and a flowchart for this Newton-Raphson method, fast decoupled load flow method as well, because once you know how to do the problem, it is easy for you to write the algorithm or write the flowchart. So hope this much is clear to you. The 3 load flow methods: Gauss-Seidel method, Newton-Raphson method, fast decoupled load flow method. The comparison of these 3 also is asked as a short answer question usually. Please just go through that as well before coming to the exam. Now, if you find any difficulty or any clarification further request, please feel free to contact me at any point of time. Thank you.